Well, welcome. Math 30-2. Today we are about to start Chapter 6, which looks at exponential functions. So here we are at 6.1, and to begin with, I just want to remind you of these different terms when we have a power. So here we have an x and then this little n that's superscripted. The way we name everything, the x is called the base. The little subscripted or superscripted n is called the exponent, and the whole thing together is called the power. Important to keep that language clear. Some people would say this is x to the power n. Meh, that's a little confusing because this whole thing is the power, the n isn't the power. So even though people use that language, better to talk about this as a base of an x with an exponent of n, so x to the n is a power. So just a reminder of terminology there. Now I'd like you to look ahead at these warm-up questions and see what you remember about simplifying these different expressions. So at this point, I'd like you to pause the video, do questions 1, 2, 3, and 4. When you're done, you can restart the video. Well, hopefully you noticed or you remembered uh, how to multiply these powers together. So let me just pull out a reminder here. So here I have 5x's multiplied, so that's this first bracket. Then I have 2x's multiplied, so again the exponent is telling me how many times the base is repeated as a factor. So here I have the base of x repeated twice in this product, and then I have just 1x. Well, as I look at this, I could count them up and say 5, 6, 7. Oh, I have 8x's, so x to the exponent 8 would be the final answer. But many of you probably remembered this shortcut, where if we're multiplying powers, and if the powers have the same base, then we can just add their exponents together. So 5 plus 2 plus 1, don't forget that 1, that we did have an invisible exponent here from this power, where there was an invisible 1 in the exponent, and that needed to be added in with the other exponents. Question number 2. Similar idea, now we're dividing powers with the same base. So again, I could list it out, but if that base was really huge, I wouldn't want to. So this is telling me I have 12 t's multiplied together. Count them up, there we go, 12. And I'm dividing by 7 t's. So I could say, well, I could count out 7 t's up here. 1, 2, 3, 4, 5, 6, 7. And those 7 t's divided by these 7 t's cancel out, which actually leaves me with a 1 in the denominator, and all of this would reduce to a 1. But that 1 would be multiplied to all of these t's that we have left over here. How many do we have? 1, 2, 3, 4, 5. Oh, t to the 5th. Excellent. Again, you may have remembered this rule. If I'm dividing powers with the same base, I can subtract their exponents and then rewrite it as a power with that new exponent. On to number 3. Question number 3, again, we're dividing powers, so I'm going to use that rule where when I divide powers, I can subtract the exponents. So I had an exponent of 5 in the numerator. I subtract the exponent in the denominator to give me an exponent of negative 9. Now, often we don't want to leave our answers with negative exponents. Sometimes it's not a big deal, but often we want to make it positive. So just a reminder here that when we have a positive exponent, like up here, this x to the 8th meant I had repeated multiplication. X was multiplied 8 times. Here, if I have a negative in the exponent, that means I have repeated division, which means I'm dividing by a 9 times. Okay, so there'd be 9 a's in this denominator. On to number 4. Now I have a power, b to the exponent 2, that's raised to a power, or to the exponent of 3. So again, I could write this out, where I have this repeated multiplication, this base, which is 2x, or b to the exponent 2, I should say, that base is repeated 3 times. And now if I use my rule from number one here, multiplying the powers with the same base, I can add the exponents. So I can add those three 2's together to give me an exponent of 6. And then it might be that you remembered this shortcut where if I have a power raised to an exponent, as in this question, then this exponent of 2 and that exponent of 3 can be multiplied together to give me this exponent of 6. So again, power raised to an exponent, I multiply the exponents. Multiplying powers, I add the exponents. Dividing powers, I subtract the exponents. So those are some of the rules for working with exponents. Just a reminder of what you've learned in previous grades. In this chapter, what we're doing is we're getting into exponential functions. Exponential functions have this form where y equals a times b to the x. Actually, the simplest version of this would give us an a value of 1, and we just have some base to an exponent. But notice that I have a variable x in the exponent. So x, which is the variable, is always going to be in the exponent for an exponential function. So the base is just going to be some number to an exponent that's a variable. So for example, I could say I have a function that would be y equals 3 times 2 to the exponent x. This would be an exponential function where this 3 would be my a value according to this formula, and this 2 would be my b value, and then I have a variable in the exponent. Now, in order for this to be a useful function for us to use, we put on some limitations. We'd say that this coefficient of a cannot equal 0, because if it's equal 0, then I have y equals 0, just a horizontal line, not exponential. Similarly, we would say that the base b has to be greater than 0, but it can't equal 1. And again, this is just to give us a useful function. If our b was less than 0, then we wouldn't get something that would be easy to graph or make use of because it would bounce between positive and negative values. And if our b value is 1, then I'd have 1 to any exponent is still 1. So then I just have y equals a times 1, which is a horizontal line, not an exponential function. So exponential functions have to meet all of these conditions. Let's look at a few examples. So here on this page, I'm going to have you do some investigating. And in this investigating, what I would like you to do is enter y equals b to the x on Desmos and add a slider for b. So the b values you'll be able to change. X is going to be values along the x-axis here. And observe what happens if you change the b values. Okay, and as you change those b values, we want to keep b greater than 1 and just observe what's happening. So once you've done that on Desmos, then see if you can predict which curves here would match which equations there. So do a prediction first, then you can enter it to double check. Okay, so pause the video here, open up Desmos, and enter y equals b to the exponent x with the slider for b, change the values of b, keeping them greater than 1, and observe what happens as b gets larger. Does your graph get steeper like this, or does your graph get less steep? So make that observation now. Pause the video at this point. Well, hopefully you were able to make some predictions and discover that this slowest growing graph will be this function a, where we have a base of 2. And this fastest growing graph, that's going to be the c, where we have this larger base value, which means the in-between one will be this dotted curve that's in the middle. So notice what happens over here as well. The a value, which is on the bottom here on the right side of the y-axis, is on the top on the left side of the y-axis. So notice it's above those other two. And then the dotted line is above A on the right, it's below A on the left side of the y-axis. So what do we observe about B? Well, hopefully you noticed that the larger B gets, the steeper the graph is, or we could say the quicker it grows. All right, let's look on down at the next investigation. This time again, I'll have you make use of Desmos. And again, we'll enter y equals b to the x. You probably still have that. Now we want to observe what happens as we adjust those b values, but keeping them between 0 and 1. So now you're going to get curves that come down in this direction when your b value is between 0 and 1. Make some observations. Once you've played around with that on Desmos, then look at these three equations. Can you predict which of these three graphs match with each of those equations? And then once you make your prediction, check it on Desmos. And then finally, what kind of observation could you make regarding this exponential equation? So pause the video at this point, and again, restart once you finish investigation 2. Well, once again, hopefully you observed that here, if I have a b value of a half, so the smallest base is going to result in the shallowest curve. So it's going to be the slowest decay here. So this would be that function for a. As this number gets, well, I guess it's as the denominator gets bigger, as the whole value gets smaller, I should say, what we get is a graph that decays or decreases more quickly. So it's going to decrease more quickly because of this small value in the base. So again, the fraction of 1/4 smaller than a half. I may have misspoke earlier. And then again, this 1/3 in between the 1/4 and the 1/2, that graph is going to be the middle one here. So what do we observe? Well, hopefully you made an observation along these lines, where the closer the b value is to 0, the more quickly the graph decays. In other words, it's steeper as it's decreasing here. So it decays more quickly. So a steeper graph going down this way when our base is closer to 0. When it's closer to 1, we see a shallower graph. It decreases more slowly. Well, let's look ahead to investigation 3. Once again, we'll make use of Desmos, but now we need to change something. We're going to use a base of 2. So you'll replace the b with a 2, and then you're going to put an a value in front of it. And this a value is what you're going to make a slider for. We're going to keep the a value positive, and again, as you drag that slider left and right for the a value, what happens to your graph? Once you observe that, then use that to predict which of these three equations matches each of these three graphs. Once you've done that, then again, make an observation that you can about how does this a value affect this exponential function. So pause the video now and work through this investigation, please. Well, hopefully what you observed is that as the a value increased, so here I have an a value of 1, then an a value of 2, an a value of 3, you may have thought the graph moves up and down. Well, it's not quite moving up and down. We'd say it's stretched vertically. And so the bigger this a value is here, the more it's stretched out vertically, so the higher the graph is. And you may have noticed that here I have a y-intercept of 3. Oh, that corresponds with the a value. This is the C graph. Here I have an a value of 2. There I have a y-intercept of 2. This is going to be the graph B. Here I had an a value that was equal to 1. I didn't write it in because 1 times anything, the 1 just disappears. But here we have that y-intercept of 1, and this would correspond to the graph A. So what observation can we make? Well, As was just stated, the a value stretches the graph vertically and gives us the value of the y-intercept. So there we have an introduction to the ideas of this chapter and how exponential functions work. On this next page, we'll just do a summary as we fill in the information that we have. So here we have y equals a times b to the x. And to begin with, we're going to summarize what happens if our b value is greater than 1 and our a value is greater than 0. This function, we would say, models exponential growth. So as we go from left to right, our graph increases, and we'd say that's exponential growth. So again, it increases as we go from left to right. And the larger the b value, the more sharply the graph increases. So here, this isn't increasing very quickly. Maybe our b value is like 1.5. But if I had a b value of 10, it would come along here and then it would just shoot up really quickly on the right side of the y-axis. On the left side, we would say that the graph approaches a horizontal asymptote of y equals 0. An asymptote is a line that the graph comes closer and closer to at its edges. So here at the left end, we can see our graph is coming closer and closer to the x-axis, which is y equals 0. On the right side, the graph is positive in quadrant 1, and we could say that the graph is approaching positive infinity. So there's the summary for when b is greater than 1 and a is greater than 0. Now here we're looking at the same function, but we have some different restrictions on a and b. Suppose our base is between 0 and 1, but our a value is still positive. Now we would say that our function models exponential decay as the graph decreases as we go from left to right. So here, as we go from left to right, the graph gets smaller and smaller, approaching again the x-axis, and we'd say that's a horizontal asymptote. So the smaller the value of b, the more sharply the graph decreases. So a b value of 0.1 is going to be pretty steep here, whereas what we've drawn here might be a b value of, oh, maybe a half, which is much bigger than 1 over 1/10. When we talk about the end behavior, we'd say the left end is positive, and once again, we could say that the left end is approaching infinity. And the right end is approaching that horizontal asymptote of y equals 0. Let's look at one more situation. Suppose the a was negative. In this case, we'd say the graph is reflected in the x-axis. So initially, up here, if a was positive, my graph increased from left to right. The left end was along this horizontal asymptote. Similarly, this left end is along the horizontal asymptote, but the graph decreases. So this graph here is a reflection of that first one, where the b value is greater than 1. Here, this is a reflection of this second graph up here, where the b value was between 0 and 1. Okay, we won't have to deal with reflections very much, but we do need to understand a little bit of what's happening with those graphs. The a value always causes a vertical stretch by a factor of a. Notice for all of these graphs, there was no x-intercept. We had y-intercepts, but no x-intercept. The y-intercept is equal to the value of a. And that's what we observed on the previous page doing that investigation number 3. The domain is all real numbers. In other words, we have a smooth and continuous curve from left to right. There are no holes or gaps in the graph. It keeps going to the right forever, and it goes to the left forever. All of these different graphs we've looked at, to the left forever and to the right forever. The range is y is greater than 0 if our a is positive. So again, those are our first two graphs up here where we said a is positive, a is positive. Our minimum value, well, we never actually reach a y value of 0. It comes closer and closer at this end, but doesn't touch the x-axis. But it does go up forever. Similarly with this second graph here with the exponential decay. There's a horizontal asymptote at y equals 0, which is along the x-axis. Now I'd like you to try this question. So complete this table given these four different functions. Just state what is the a value, what is the b value, and then what's the y-intercept for each function. So pause the video at this point, restart once you've finished this table. Well, hopefully you got a graph that looks, or you got a table filled in the same as mine. Here there's nothing multiplied in front of the 3, so the a value is a 1. Here I have a 2 multiplied in front, so my a value is a 2. The 5 gives me an a value of 5, and the 0.5 gives me an a value of 0.5. For all of these, the base was 3, so that was the b value for all three of the functions. And then the y-intercept, that is always the same as the a value. So whatever I had up here is going to be the y-intercept down there. A value, y-intercept, a, y-intercept, a value, and the y-intercept. All right, there are a few questions for you to practice from this section. Not a lot, but you can take some time, work through those before continuing on to the next lesson.